The final project that I've done for a Coursera course that I took, which was machine learning for product managers. And in this project, we had to build a model to predict the electrical energy output of a combined cycle power plant. And it uses a combination of features like gas turbines, steam turbines, and heat recovery steam generators to generate power. And we had roughly around 9.5K hourly average ambient environmental readings from sensors at the power plant, which will be used in the model. So here is a list of all the features that are going to be our input features, like temperature, ambient pressure, relative humidity, exhaust vacuum, and the last one is the target variable, which is the net hourly electrical energy output that we want to predict. There were 5 major model process steps that I undertook, which was starting with defining the ML approach and evaluating the metric, feature selection and algorithm identification, followed by data splitting and validation strategy, and then it was the model comparison and selection, and finally a model evaluation and performance assessment. So looking quickly at the flowchart or the algorithm for predicting the energy output, we start with loading the data, which is importing it from the Excel file, which includes all the features of X and Y variable. Then we perform a correlation analysis to identify the relationship between the features and the target variable, and we also visualize the correlation using a heat map. Next, we select the features of the model with significant correlation to the target PE. Next is splitting the data into training and test at 80 and 20% using a train test split. The fifth step is the validation strategy, where we implement a cross validation to ensure robust model evaluation. Since we have a very small data set, we have to do this. Also, we define a function to calculate the root mean square error using a 5-fold cross validation. Followed by this is the model comparison, where we choose linear regression and random forest. We have to train the model using the training set and then calculate the cross validation root mean square error. The next is the hyperparameter tuning, an additional step that we can include to best combine the hyperparameters of random forest model. Now finally, we train the best model on the entire training set, predict the test set. Now finally, we calculate the root mean square and R-square on the test set to evaluate the performance. Why RMSE? Because it gives an error value in the same unit as the target variable, and it will be very easy for making it to interpret. Finally, we can visualize the predictions of the actual and predicted values. This is the same thing in terms of the algorithm, where I've mentioned all the specific line of code which is used for the data load, correlation, feature selection, splitting, cross-validation, etc. So this structured approach will ensure there's a systematic workflow from the data preparation to model evaluation, providing clarity and facilitating better understanding. Here is the result of the correlation matrix, and on the right we have the actual and predicted output. We can clearly see a very neat and clean graph on the right. We also have the correlation matrix, where the red ones are highly negatively correlated. Okay, let's evaluate the ML model results. So first, the correlation matrix. Ambient temperature and energy production show a very strong negative correlation, indicating that as AT increases, PE decreases. Never mind. So volume also shows a strong negative correlation with PE of minus 0.86. Air pressure has a positive correlation of 0.51, and relative humidity has moderate positive correlation of just 0.389, which is slightly weaker than the others. Now let's come to the model performance bit. Linear regression's root mean square error was around 4.57, which is like an average error per prediction on the cross validation data. It indicates that On average, the predictions for the energy output have an error of approximately 4.57 megawatt. So this suggests that the relationship between the input feature and the target may not be purely linear, perhaps. So when we evaluate the random forests RMSE, it shows a slightly lower number of 3.46, which suggests a better model performance. And also we see that it can capture the non-linear relationships between the features and the target more effectively, especially because one of the features, relative humidity, was only moderately positively correlated to our output variable. Now the final random forest model that was generated using the grid method, it has an even better and improved RMSE of 3.223 from the cross validation error, and it definitely indicates a well fit model with a very high R square of 0.96. It's a strong result indicating the random forest model explains 96.4% of the variance in the target variable, which is excellent for a regression task. Now, when we compare the two, definitely random forest outperforms the linear regression model in terms of RMSE, and a lower RMSE in the random forest, it signifies that it's more accurately predicting the values of the output variable, and it has the ability to handle complex and non-linear relationships. So we can conclude that it provides a more reliable prediction with fewer errors, and it outperforms the linear regression in predicting the output variable of energy production. Also, a high R square value is suggesting a better fit for this data set. And the correlation between the variables also provides a good insight into the relationships driving the model's predictions. So thus, for this data set, it seems that random forest should be considered as the final model to use, owing to its higher, superior performance in capturing the underlying patterns of the data. Thank you.